Hi everyone, welcome back to the transport phenomena class. Today we will discuss about the second example on mass transfer. In this case, we have two connected vessels. In this vessel, we have pure gas A, and in this vessel, we have pure gas B. Those vessels are connected by pipe with the length of L. In the middle of the pipe, we have one initially closed valve. When the valve is open, gas A will diffuse to the vessel B, and gas B will diffuse to vessel A. Now the question is, can you determine what is the profile of XA along the pipe? One more important information is, because the volume of each vessel is huge compared to the volume of the pipe, so at this point we can assume that XA equal to 1, and at this point we can assume that XB equal to 1. Okay, to solve this problem, first we need to draw the control volume. This is our control volume. Here we have A in at Z and A out at Z plus delta Z. The shell mass balance can be written as follows: NA at Z times the perpendicular cross sections minus NA at Z plus delta Z times the cross sections equal to 0, because this is a steady state condition. Divide this equation by S delta Z, we can get minus dNA over dZ equal to 0. Now we have to find the relationship between NA and JA. In this case, A will move to the right and B will move to the left. So the direction is opposite. I can write that NA equal to minus NB. Minus here is to show that the directions is opposite. How about the amount? I believe in this case, the amount of gas A moved to the right and the amount of gas B moved to the left must be the same. Otherwise, one tank will undergo overpressure and the other will undergo shrinkage. Okay, so the amount must be the same. So finally, we have NA equal to JA equal to minus diffusivity of AB times the concentration dXA over dZ. We can substitute this equation to the one that we got from the shell mass balance. That gave us the equations d over dz dABC dXA over dZ equal to 0. The concentration of ideal gas at constant pressure and constant temperature must be constant. And the diffusivity of AB will not change much, so I can move concentration and diffusivity and assume it as constant. The first integration will give us dXA over dZ equal to constant 1, and the second integration will give us constant 1 times Z plus constant 2. To solve this equation, we need two boundary conditions. The first boundary conditions, at z equal to 0, xa is 1. And the second boundary condition, at z equal to L, which is the length of the pipe, xa equal to 0. Okay, at z equal to L, we can say the mole fraction of A is equal to 0. Because if we draw the line, this is z equal to 0 and this is z equal to L. Okay, at this point, we know that xb is 1, so that will give us xa equal to 0. Using these two boundary conditions, you can solve this equation and you can get the equations to show the profile of xa along the pipe. That's all for today. Thank you for watching and see you on the next video.